Thank you all very much for coming. It's a pleasure to introduce our first speaker of the day. You all know there's a second seminar at 3. And we're going to start the morning with NORA TISCHLER, who until recently was in Australia, now is an experimentalist. Now she's a theorist with Jens Eisen in Berlin, and might become an experimentalist soon again. And she will tell us a bit about more theoretical work.
Yeah.
About a provable accuracy advantage in machine learning based quantum models.
Okay. Yeah. So, yeah. Thanks all for coming. I understand that there's another seminar today, so it's extra effort. Thank you. It's a real pleasure to be here after so many years. Last time I presented here was for my PhD defense. And yes, it's also my first real in-person talk for a year and a half, so it's pretty exciting. Now, you were slightly tricked because I've changed my title slightly. You might be wondering, okay, I mean, this talk was announced yesterday. How could I have changed my mind so quickly? I basically learned, that there could be a wider audience, and so I tried to widen the scope a little bit. And so now I'm also including some of the earlier experimental work, but that's in the same overall topic. So yeah, so now the title of my talk is Quantum Advantages in Simulations of Classical Stochastic Processes. Okay, and so basically what I'm presenting is based on these 3 papers here. So you can see all the collaborators there. The first 2 papers were experiments carried out in Jeff Pride's group, and they were also in collaboration with a theory group from Singapore, Milo Gu's group. And then the third paper, so these first 2 are published, the third one is on the archive. The third one is theory work. That was a collaboration between lots of people, as you can see, so affiliated with NTU and NUS in Singapore and Stochastic in China. And a shout out here, we've got also Ikoki's very own Andy. Okay. All right, so, I mean, given where we are here, you're all aware of the fact that quantum effects can be used to enhance certain tasks, like a variety of different tasks. And some well-known examples are cryptography and metrology. And a maybe less well-known task is the simulation of classical stochastic processes. And that's what we'll be looking at today. All right, so just so that we're all on the same page, you can basically think of this as a kind of spectrum where on one end you've got deterministic models like, calculating the trajectory of some ball or something. At the other extreme, you've got something totally random like tossing a fair coin where you have no idea whether you're going to get heads or tails. And in between, there's many, many processes like the weather, the share market, and so on, which are partially random. And so everything here, except for the very left, you consider a stochastic process model. So basically, generally, you don't know the kind of complicated dynamics that are going on the inside of the process, but what you do get access to is a sequence of outputs. And so this is basically what you're interested in and what you're trying to predict. And yeah, by the way, I've already said at the beginning, but just to repeat, feel free to ask questions also during the talk. It's basically like half an hour long by itself, so there should be some time for questions. Okay, so a model of a stochastic process should accept information about the past and then tell you about the future statistics. So we'll be looking at discrete time processes, and so if the output is like a binary variable, then the past could look something like this, and the model should tell you all the different futures that can occur and with what probability each one happens. A simulator will just pick one of the outputs according to the correct probabilities. And so basically it's sampling this future statistics. Okay, now I've already hinted, I guess, at the fact that there's a sort of thing of quantum enhanced simulation. So the first question there is, where does the quantum come in? So, I mean, these outputs are classical data both in the past and the future statistics sample as well. and they remain classical, but the simulator, instead of it being a classical information processor, you can replace it by a quantum information processor. And so you'd hope that by doing that, you're gaining some sort of an increased performance or of some sort, or some advantage. Okay, and so what is it that we're trying to enhance? Actually, you can look at different things. People care about different things. So on the one hand, we've got a kind of a measure of efficiency, which is how much memory does the simulator need in order to produce the simulation. And people care about this because it's kind of like a fundamental resource, but also the minimum memory that you need is kind of fundamentally tells you how much information about the past is needed, so how efficiently the simulator uses the information from the past. On the other hand, here, of course, I mean, if you're creating some sample of the future, obviously you want that to be accurate. So there's also this aspect of accuracy that you want to maximize. Okay, and so basically this talk will be about both of these things. So first we'll look at the memory requirements for exact simulation, and then we'll look at the accuracy aspect. Okay, so how do you actually picture a simulator? So generally, the sort of simulators that we're looking at, or sort of models that we're looking at, there's a systematic procedure where, given some past, you have to be able to map it into a memory state of the simulator, and then you have to, through systematic action on that memory, sequentially be able to produce outputs for future time steps. So, for example, if you have a classical simulator, you can think of it in this way, where the green thing here is the memory. It goes into some computation step that spits out the output for the first time step, and then gives the updated memory to the next time step, and then you can repeat that. And a quantum simulator, the sort of quantum simulators that we're looking at, actually work very similarly. So you can see the parallel here. But basically now, we've got a unitary interaction between two systems. One of the systems here is still the memory, so now this is a quantum state. And the other system that we feed in is an ancilla, so it's in a fixed state, it contains no information going in. It's like a blank tape, basically. And then the unitary gives you two outputs. So one system you measure in the computational basis to get like the output for that first time step, and the other one is now the updated memory, which you feed on to the next time step, and so on. Okay, so now we're looking at sort of memory, the amount of memory that's needed. So the amount of input information, so if you've got some specific past, you need to initialize your simulator. So you need to somehow take information from that past and like encode it in the memory. And the amount of input information that the simulator demands for exact simulation, so where you have perfect accuracy, that is called the statistical complexity, so the entropy. And people think of it as a very like fundamental like property of the process itself, because this is optimized over all models. So, you know, it basically relates to, like, people think of it as relating to the structure of the process. Now, this was all like pretty neat until in 2012, Milo Gu and co-workers started looking at quantum information processing, and they found that basically the complexity of a quantum model is smaller than, or at worst equal to, that of a classical model. So there's this sort of memory advantage. Okay, so where does this come from? I'll just basically give you like the essential reason behind it. All right, so this is also true for classical models. Basically, if you have your set of all pasts, then it can happen that two pasts, although they're distinct, nevertheless share exactly the same future statistics. So for example, if you've got some, you know, limited Markov order, then if the paths differ in the distant past, right, it doesn't have any effect on the future statistics. And so basically, you don't need to distinguish between those two. And so in this way, you can divide the set of all paths into these equivalence classes, and they're called causal states. And so that's basically all that you need from the past. Okay, so two paths are in different equivalence classes if they don't have identical future statistics. But, I mean, it can happen that there's some overlap in the futures. They're just not exactly the same. But in classical encoding, you need to encode those two causal states orthogonally. By contrast, in quantum encoding, you can use non-orthogonal states in general, and this will reduce your entropy and therefore lower your complexity.
So then you mean is you're going to do some compression or something?
Yes, exactly. And I'll come back to that. Yeah, absolutely. Okay, so let's look at a just very basic example. This is called the perturbed coin process, and you can think of it as a coin in a box, where at each time step you shake the box somewhat, and then you check whether it's in heads or tails. Say heads is 0, tails is 1. So then you get an output. And doing this many times, you produce a bit string. And basically, this is the model of this stochastic process. It's very simple. So it's a Markov process where all you care about, I mean, is the last thing you've observed. So if you start in heads, there's a probability of L of remaining in heads and 1 minus L flipping to tails. And if you start in tails, you have a probability of M of remaining and 1 minus M of flipping. So this is basically a family of processes parameterized by M and L. All right, so the quantum simulator of this process, basically you can think of it this way. So there's one qubit. We've got two causal states. So what I've shown here, these are the two causal states. And so we encode them in a qubit, generally non-orthogonally. Now, how much overlap is between them depends on the process parameters M and L. But basically, so this is the memory that we initialize based on the path that we're given, but we really only care about the last observed output. And so then we have these ancilla qubits. So these are all in the logical 0. And then we have an interaction between the memory and the first ancilla. So this is some general interaction. Then we measure one output. That gives us the output for that time step. Here we have the updated memory, and then we repeat. And so the memory is basically going down and down. And no matter how many time steps we do, we should then have here the updated memory, which is in the quantum causal state that's appropriate for that new past. Okay, so the first experimental demonstration of this sort of, at the time, new quantum advantage was done in Jeff Pride's group, but before my time there. And it was done with this experiment here. And basically, what they did was they had two photons. One corresponds to the memory and one to the ancilla. And the qubits are encoded in the polarization. And then they performed a probabilistic, like linear optical, two-qubit interaction here. And then you get a photon out here, one out here. So one you can measure, that's your output, and the other one is the now updated memory. Now this was, like it did, they were able to show the advantage, but I mean, you've basically used up, like you had two photons, you've used up one and the other one now. Realistically, there was no way in this experiment to then do multiple time steps. But in general, you want to be able to simulate over multiple time steps. So this was the first thing that I was involved in that we looked at. So basically, for example, in this process, if you go over 3 time steps, then there's 8 different trajectories. And so that's quite a lot of photons, you'd think, a little bit tricky. But we came up with a different way of doing this. And so basically, we used this setup here. And we just used a single photon. And we encoded all of the information in the one photon. So the polarization of the photon was playing the role of the memory. And for all the ancilla qubits, we encoded them all in a high-dimensional degree of freedom, the arrival time. OK, and so basically, a photon goes in, then the correct polarization, which is the memory, is prepared. And then each of these blocks here corresponds to a time step in the simulation. And basically, what you've got is a controlled operation between polarization and time. So you can either take a short or a long path in each of these time steps. And so then by the end, if you measure the arrival time of the photon, you know which path it's taken, and you get all three, like the outputs, the classical outputs of all three time steps by measuring the arrival time. And the polarization, you know, is the updated memory at all times. Okay, so yeah, so this is basically what we end up with here. All right, so the first thing you want to do when you build a simulator, I mean, if you're hoping for quantum advantage, you have to go back to basics and actually check if it even works properly. Because if not, I mean, there's no point in talking about a quantum advantage. And so you basically want to have the correct statistical futures produced. And this is what we're checking here. So on this graph, this is the process parameter M. So each color corresponds to a different process in this family. L is fixed. And then on this axis, we've got the 8 different outcomes that you can get over 3 time steps. The height is the probability of that outcome occurring. And basically, there is these see-through bars, which is the ideal theoretical values. And then the colored bars are the experimentally observed probabilities. And already, as you can see by eye, they match reasonably well. So the classical fidelities over these probability distributions are all above 99%. Okay, so then coming back to the quantum advantage, what we look at here is, so this is coming back to this kind of Schumacher compression, the complexity, like the entropy of the stationary state. So classically, it's the Shannon entropy of the stationary distribution, and this blue line is the best, corresponds to the best possible classical simulator you can have for this process. Then for the quantum case, the equivalent is the von Neumann entropy of the stationary state. And basically the line is what we'd expect, and then the data points are what we see in the experiment. And so you can see that there's a clear memory advantage there. Okay, but now coming back to this compression issue. So what you've seen so far, you basically had 2 causal states. So you need 2 states, classically and quantumly. Classically, you've got a bit, and in the quantum encoding, you encode into a qubit. So if you had an ensemble of like a lot of simulators running in parallel in the IID case, then you could do like clever encoding to actually save like physical resources. But if you just have one individual simulator, I mean, then you still have a 2-dimensional memory in both cases. And so then a natural question was to ask, can you get an advantage already on the level of an individual simulator as well? And for that, we need a more complex process. And the one that we look at here, I mean, I won't go through the details, but the main thing to note is that it's got 3 causal states, S0, 1, and 2. Again, with some transition probabilities between the states and so on. But so now, classically, you need a 3-level system to encode. Or if you're sticking to bits, right, then you need 2 bits. But for the quantum encoding, the overlap between the different causal states is such that actually you can fit all 3 into a qubit encoding. And so this means that it's actually possible, like in theory, to have lower dimensional memory. Okay, and so this experiment was a bit more involved than the previous one I showed you. So basically, this is sort of the circuit that we want to implement. So this is the memory is here. This is the 2-dimensional memory. And then it needs to be fanned out into a Q-trit, because in the end, you've got 3 different symbols that you can output, so it's no longer a binary variable. So you want to be able to measure something and get one of 3 outcomes. So that's what's happening here. And then you need to do a 2-qubit interaction, or not qubit, a Q-trit qubit interaction to prepare the memory for future time steps, basically, for it to be in the correct memory state. And so this, with linear optics, is a little bit involved, because basically we've got, we can have multi-photon interactions, probabilistic ones, that we can post-select. And this is like the sort of thing we're doing here. But the issue is, the way you post-select is by making sure that there's a photon in each of specific output modes. And so if you just had this, what could happen is a photon, for example, from here could go down and then could go back up. And so if you post-select at the end, it will look like everything's fine. There's a photon in this system and one in this system, but actually you had two, like you had a failure. And for that reason, we needed to introduce another photon here and do a kind of a non-destructive measurement that's more or less checking occupancy of that mode. And because we get photons in pairs via down conversion, we actually, it was a 4-photon experiment where one of the photons was just a trigger. And so this is the setup for it. This was done at telecom wavelength with superconducting nanowire single photon detectors. And this is where all the gates happen here, essentially. Now, the key thing here is that the memory is encoded at this point into the polarization of a single photon. So it is necessarily two-dimensional. But we know that for the optimal classical simulator, we'd need a 3-level system. So, so that's kind of like the key point of this experiment. But once again, we want to check that the simulator, like the statistics that we produce are correct, and then we want to characterize the memory saving. So again, the fidelities, like the classical fidelities between the probability distributions are above 99%, and the quantum fidelity of the stationary state with the ideal one is also above 99%. So we're pretty happy with how the simulator works. And then in terms of the memory, I already pointed out the main thing, which is the fact that we encode in polarization. So this was like one of those weird experiments where you don't really need to have like a results figure, because, I mean, there is like, once you encode in polarization, you've got that dimensional advantage. But of course, it's still nice to produce some figures. And so basically, we looked at, well, first of all, we carried out the simulation for lots of different processes in this family characterized by P and Q in this case. And so this is what we expect in theory. I don't know if you can see it very well with this projection, but there's an upper surface, which is the best classical simulator, what it can achieve. So again, this is statistical complexity. So this is not just dimensions. This is, again, this kind of entropic ensemble quantity. And then this lower surface is the quantum simulator that we're trying to produce. And so then we take a couple of different cross sections here, and that's what we're showing here. So not only do you have a dimensional advantage, you also have an entropic advantage. Yeah?
Can I ask a question? Because it's like you say, like the fact that it's in a 2-degree of freedom photon is proof enough. But the thing is, like, how did you convince yourself that the statistics are right? Isn't like statistically, what was your how good did it have to be before you said, yeah, this is
yeah, so I mean, so there's, yeah, so I mean, this is a good point. We are trying, I mean, we're comparing with what you'd need classically for exact simulation, and I mean, quantum mechanically, so this is basically why we're checking these probability distributions, and so we're just comparing how well it fits what it should fit. But it's true that, like in these graphs, the black line, which is the theory bound, this is assuming exactly ideal simulation. And so we want to be very close to ideal, but experimentally, you're never going to be exactly there. So in this experiment, we didn't look at errors, but in the next part of the talk, we'll discuss that more. So here we just kind of left it as, you know, this advantage is huge, and we're, you know, pretty close to ideal, but we didn't really quantify how far, as in, like, we quantified how far off we are, but we didn't look at what effect that has on the ideal simulator. Okay, so maybe I'll go back to this figure. So not only do we have a dimensional advantage on the one hand and an entropic advantage on the other hand, actually something pretty cool happens in this shaded red area. And so what happens there is you don't just have these advantages individually. The quantum advantage there is so strong that even if you had lots of simulators, and even if then classically you allow clever encoding strategies to save memory, but for the quantum counterpart you don't, you would still have an advantage. Okay, so now let's switch gears and look at, so far we looked at this memory requirement for exact simulation. Now let's look at this other part, which is the accuracy. So we want to know how faithful the output statistics are to that of the real process. And the way we quantify this is, well, we call that distortion, is a deviation of our model's probability distribution over futures compared to that of the true process. And then the way that we quantify the deviation is as the Kullback-Leibler divergence averaged over all the paths in this stationary scenario. Okay, so why? I mean, like, why did we set out to do this? Basically, up until everything that I've shown you up until now, you were always expected to already know what the process is. And only exact simulation was considered. So as I mentioned, like, this is why we were trying to make sure we are very close to the exact simulation, but yeah, you were basically assuming that your outputs were perfectly accurate. However, if you go out into the real world and you observe some stochastic process, you know, normally no one tells you what the underlying model is. What you actually have access to is the output of the process. And so what happens if you don't know the underlying model? And then also, I mean, so for some processes, as you go to larger sizes or change some parameter, your memory that you need can grow to infinity. And so clearly it's a resource that like is restricted in terms of physical resources. So it's important to look at what happens if you restrict your memory to something and then maybe you're no longer able to model perfectly. Also, if you start off with just the output of the process, then if you allow infinite memory, like, you might also overfit and, you know, and accidentally fit to some noise that you shouldn't be fitting to. So this is why it kind of makes sense to look at a limited memory scenario. And so basically our motivation was to come up with an algorithm that can learn a quantum model based on just output data, so like a sample of the process, and it should accommodate memory restraints. And then the scientific question that we are trying to answer is whether in this setting using quantum information processor can give you an accuracy advantage. Okay, so now you're already familiar with this sort of quantum simulator. So this is the same sort of thing here. And basically, our learning algorithm as inputs takes a sample of the output of the process, and we tell it what dimensional memory we allow. And then the output of this learning algorithm is a quantum model. So a quantum model which can then turn paths into futures. The way that a quantum model is specified is you have to know what the unitary is, which you here repeatedly apply. And you have to know the encoding map. So that's maybe not as obvious in this figure, but I mean, here we've got a quantum state at the input that we initialize the simulator with. So we essentially have to have a map that tells us, given a certain past, how do we prepare, as in what quantum state do we prepare? Okay, so this is an overview of the algorithm, and I won't go into like a lot of details here, but I'll just point out some of the main things. So first of all, I mean, so we're using atom optimization, this is like a fancy type of gradient descent. And so this means we need to have some cost function that we are trying to optimize. So for that, I mean, ideally, you'd want to optimize the distortion itself. But I mean, that relies on like the ideal process, which you don't have access to in practice while we're training. I mean, we don't want to need to know the real process model. And so we actually use a proxy that is only based on that like sample that we're given, and it's basically this negative log likelihood of producing the sample with the quantum simulator model that we have. And that turns out to work quite well. Okay, so then what is the thing that we're optimizing? It's actually like a set of matrices here, which are just, I mean, they are dq by dq complex matrices, where dq is the memory dimension that we allow. And it's a set of matrices. The number of the matrices is the number of the alphabet of the output, like how many different outputs you can get. And we don't put any constraints, they're just general complex matrices. And then afterwards, after we've optimized, we can recover the completeness relation to get a set of Krauss operators. And those are basically, like these operators tell you what happens to the memory as you interact with an ancilla, and then afterwards you measure and you get a outcome X. And so from those cross operators, we can then get the unitary and the encoding map. And so that's basically then the model specified. Okay, so this is so far very general. And so, I mean, this algorithm can be applied to lots of different processes. So we wanted to try it out on some stochastic processes. And I'll just show you some examples. So the first here, it's called the quasi-cycle process. It plays a role in thermodynamics. And this example that we're looking at here has got 3 causal states. And it's characterized, it's parameterized by P and delta. And so because it's got 3 causal states, it does not one of those special cases where qubit is enough. So generally, you would need a 3-dimensional system for exact simulation. But we restrict the memory to a 2-dimensional system, and so basically then see how much that distorts the statistics. So, I mean, the colors don't show up super great, but I guess it's okay. So what we show here is, so these are the process parameters, P and delta. So each pair here specifies one process out of this family. And then the color here is the distortion. So on the left, what we have is a bound on the distortion the best possible classical simulator can achieve. And you can see, I mean, so this blue area is like large distortion. But then on the right, what we're showing is the distortion that our actual machine-learned quantum simulator achieves. And so you can see that like, the distortion is lower, and it's sort of up to an order of magnitude lower. Okay. Yeah, so then here's another process. This is called the uniform renewal process, and you can kind of think of it as an interpolation between like a discrete ticking clock and a Poisson process. So basically what happens is, this is sort of like the reset. When you go to S0, you click, and then you kind of go along this for a certain number of steps. I mean, that's unknown. And you don't click when you go along, but then as you go back to S0, you click. And the number of time steps between 2 successive clicks is uniformly distributed. Okay, so basically here the process parameter is n. So n tells you how many causal states you need, as you can see in this figure here, for exact simulation, that is. All right, and so what we're showing at the bottom here is n on this axis, and here, this d is the memory that we make available for the simulator. So again, on the left, we've got a bound on the best possible classical simulator. And as you can see, if d equals n, then you can simulate exactly. So once you restrict d to something lower, then you get some distortion. On the right, we've got our machine-learned quantum model, the distortion that it has. And as you can see, in general, you've got lower distortions again, so that's an advantage. But you might, I mean, the colors don't show up very well with this projector, but here there's one square that's actually a bit darker, So you might be thinking like, wow, it's performing worse, and that's true. But you have to remember that you're comparing like the actual machine learned quantum model with, it has a handicap because it was trained on a finite size sample. Whereas for this bound on the classical simulators, we assume that we know the process perfectly. Okay, now all these like distortion results that I've shown, they're basically, I mean, the way this works is we optimize these matrices. This is all done in terms of like numerics, in terms of numbers, and then we assume that the implementation of this quantum simulator is perfect. But, of course, if you implement on an actual physical device, you will always have some additional noise. So then it's a valid question to ask, I mean, will this accuracy advantage still survive like a real-world noisy implementation? And that's what we're checking here. And so this is a bit of a different type of experiment to the ones I showed before, because this none of us did physically. So this is on one of the IBM quantum computers, like the cloud ones. And what you can see here, the yellow bar is the bound on the best possible classical simulator. So this is the case d equals 2, n equals 3. And blue is what we would expect for a machine-learned quantum model if it was implemented perfectly. So this is like what we aspire to, so to speak. And then this orange bar is what we actually got from the NISQ implementation. And now, as you can see, I mean, as you would expect, it's worse than the ideal one because there's some noise. However, it is still statistically significantly better than any possible classical simulator you could implement. I mean, even if it was implemented perfectly. So once again, like the comparison is like kind of on the harsh end, right? Because we are comparing with a classical simulator where the process is known and the implementation is perfect. And I mean, even a bound, like maybe real ones could even be worse. Okay, so to kind of wrap up, we've looked at different things. So for the case of exact simulation, you've seen that you can have an entropic and a dimensional memory advantage by using quantum information processing. And I mean, so the demonstrations we did, okay, you might be thinking like, all right, we got a qubit memory instead of like a q-trit memory, but like maybe that's not like huge, but in principle, you can get for other processes, you can get an unbounded advantage. So it's not limited to stay in this kind of small scale. Okay, and so then the other thing we looked at was now no longer insisting on exact simulation, but instead fixing the memory and then incurring some decrease in accuracy. We've presented a general method that can learn quantum models based on like real data. Now, it's, I guess, worth pointing out, so sometimes in the quantum machine learning literature, you find works where it's very specific to one contrived example only. And so in this sense, our work is nice because it can be applied to lots of different processes. So it's not like it was tailored to just like work for one specific process. We tested it on several processes. I've shown you some examples here. And then we've shown an accuracy advantage compared to the optimal classical simulator. And there it's worth pointing out, once again, I mean, like the easy thing to do would have been to just, say, compare our machine-learned quantum models with some machine-learned classical model. I mean, that's kind of like what you'd naturally think to do. But then you can't say anything rigorous because you don't have a guarantee that that machine-learned classical model is actually optimal. And so that's why it's really important to have rigorous bounds so that you can really make a clear statement about advantage. And then we also experimentally demonstrated it on a NISQ device. And we showed that the accuracy advantage still survived noisy implementation. Okay, so that's it from me. If you're interested in more details, I mean, I'm here to answer questions, or you can look up the papers, or if you think of something later, also feel free to email me. I'm happy to answer questions later as well. Thanks. No,
The
yeah.
presentation was clear, but that means we've got time for questions. So okay, so I had a question concerning the advantage and accuracy that
Yep.
you've shown on this IBM quantum
Yeah,
simulator.
yeah, yeah.
I know it's like machine learned, so it's probably very hard to say anything rigorous, but do you know anything about the scalability?
Yeah. No, so this is a very good point. So, I mean, first of all, right, I wasn't, yeah, so maybe just to clarify, we do, right, like we do the machine learning numerically by classically describing quantum, like unitaries, matrices, and so on, right? And then after, so that's the learning happens sort of first. But then afterwards, once we have the model, then the implementation is sort of separate, and so that memory advantage really applies to the implementation itself. And so it's this, so we didn't do the learning on the IBM machine, we did the implementation on the IBM machine. And so there, I mean, like the way that these bars come about is just like ran it many times, and collected statistics and so on, and then like got like the different probabilities and so on. But in terms of scalability, like this is a very good point. I mean, the issue is if you just try and do exactly this and try and apply it to large systems, like to lots of qubits, right? Then doing this classical description of the quantum simulator becomes very difficult. And so in exactly this form, we're somewhat limited to small systems, but I mean, to be fair, you can also have like a really large advantage, for example, in memory, even in small systems. So just being restricted to small systems doesn't necessarily mean that you can't have like a large advantage or something like this, but of course, like the types of processes you're simulating is then limited. So the next step would be to actually make the learning part also quantum.
Yes, I mean, what you're saying I completely understand, but it's for a generic process, right? But if you have a very specific process, can't you extrapolate and kind of find the best quantum model even for an arbitrary dimensional system?
Yeah.
You should be able to derive it analytically even with classical machine learning, and then...
Yes, but if you, okay, I mean, but then you don't need the learning essentially, right? Like the stuff that I was showing earlier, right? If you observe the process and you basically understand the process and you know how to model it, then then you don't need to, then you might be able to extrapolate without doing that type of learning.
Sorry, there are more questions.
There's a question, but can I respond to Marcus's point? So actually, there's two things coming. One is like finding the optimal quantum model is just not solved for anything other than the absolutely like two-dimensional classical processes.
And
so
yeah, two and three dimensional, I guess. Yeah.
It's just because finding these models and making sure and even proving if they're optimal once you found them it's just so mathematically hard that it just hasn't been done yet. And the second is like to go back into the scaling, like it's still okay even if you say the best I can ever do is like a 5-qubit system or something like this, because there's like most processes even like scale extremely badly, and so you can have processes which might require like an unbounded number of classical degrees of freedom. So an example would be I'm trying to model a bead on a ring that moves into Brownian motion, and I store the location of the bead as like various points, and like you can have quantum models which do this with like some finite number of qubits, whereas to describe it classically, you need to be able to store a real number to like arbitrary precision.
That's right. So even if you're limited to small systems, you can have a large advantage. So like interesting stuff can already happen with small systems, but I mean it still would be interesting to be able to go to large systems as well.
Yeah, no, but I mean, sorry to continue this discussion, because here the comparisons have 5 classical bits of memory versus 5 qubits of memory.
Or in that figure, I mean, or I mean it's even less because it's like these are dimensions.
5-dimensional systems.
Yeah.
It's like 2.5.
Yeah. Well, it goes to 4 there, but yeah. Mhm.
4.
Yeah, 4.
I may accidentally this kind of silly question, but I will ask it anyway.
Yeah, yeah.
So I don't really know anything about it, so I'm sorry for this silly question, but so you were talking about this machine learning and so on. The result that I really get from this machine learning, is it like a unitary matrix, or what is it?
So you get, in the end, what you need is a unitary matrix and an encoding map. So a map that you, like if I give you a past, like a sequence of past outputs, you need to know in what state to prepare the memory. The way we get it is via like first matrices, then like turning those into cross operators, and then from the cross operators we can deduce the other things.
Okay. Because it was not really clear to me. You were talking about this quantum process, right? And so
Yeah.
compared with the classical process. But
Yeah.
what are the actual things that you compare then?
Well, so I mean, the things that we compare here are these distortions. So that's how well the statistics that are produced by the simulator match the true process. And so we can do this here because, I mean, you know, in this case, we made the data, like we have a specific true process in mind, and then so that then in that case we can compare.
Okay.
But the knowledge about the true process didn't go into the learning part.
Yeah. And so, like, so that's the
Yeah.
last question. So what you get in the end is that, say, this unitary matrix and it's encoding.
Yep.
And so there is a whole bunch of additional work necessary in order to refine an implementation of this unitary experiment.
Yes, I mean,
I mean,
right, it depends on,
the computer is probably already done. Like,
well, like, I mean, it depends on the system that you're working in, for example, right? Like, but like, yes, in general, so all you have is the unitary, and then you would want to map it to some implementation, but depending on what platform you use. So in our case, for example, the way I didn't show this, but the way we implement this, so because we're in the, so n is 3, d is 2, so we have 2 qubits that the unitary is happening between, and so on this quantum computer, we had some controlled operations and then and then 6 single qubit rotations, and those single qubit rotations are the things we optimize to then get close to implementing the correct unitary. So yes, there is an extra step that I didn't mention, basically. Yep.
I have a potentially silly question. So, I mean, the advantage, if I understood correctly, lies in like the dimensional advantage, in the fact that the state space of the qubit is basically continuous in the sense that you can go from 0 to 1 in a continuous fashion.
So then, yeah, in a sense, yeah.
Whereas if you use classical bits, there's always some sort of for any finite number, a discrete set of different states you can sort of tell apart, right? But then in the quantum case, that would mean that in any experiment, you're basically limited by how well you can resolve the difference between 2 non-orthogonal states, right?
Yeah, so for example, that example that Andy mentioned, where you can get like an unbound, like you would need, some huge precision to store classically. There, you do then need really high experimental precision to be able to like basically resolve very similar states. So yes, there is that aspect.
Right, so would it be a fair comparison to, for instance, identify, what this precision exponentially is, like how well you can?
Well, I mean, so in
coarse graining essentially.
So I mean, if your precision is not good enough experimentally, this will show up in the statistics, right? And so this is why we always check if the statistics we produce matches closely the statistics that we're trying to produce. So if the experimental precision was not good enough, it would basically show up there. And I mean, there are some, like if you look at the experimental versus theory plots, there are some offsets, and this is because of sort of experimental limitations.
Right. So then if one were to sort of, let's say, fully exploit as much as one can this dimensional advantage, right? Then at some point one would expect that as the dimensional advantage increases,
Yeah.
the accuracy would just go down.
Yes, so exactly. So given some limited experimental accuracy, so limited, experimental accuracy, the memory advantage you can achieve will be limited. So where in theory you can go to unbounded, in practice it will like taper off somewhere. Yep.
There might be a computational mechanics point here, which is when you store things in these non-orthogonal states, like this means you can no longer distinguish like which encoding you put it into, which means that you can't tell the pasts apart. But it might still be like you didn't need to be able to distinguish them in terms of their future behavior. And so the general game for this sort of quantum computation mechanics is if you have processes with like overlapping statistics in the future, you can store them as overlapping quantum states.
Yeah.
Because you don't need to be able to distinguish them. So it's not like, oh,
yeah, this is basically.
We cared about when we made this.
Yeah.
So like, so to go back to the theory, not the experiment, the theory of this linear example, like it could be that you have a provably finite amount of like quantum dimensions to store something that takes an infinite classical one, because you just don't need to be able to distinguish exactly what it was encoded into, so long as when you measure this example is the correct from the correct problem distribution in the future. I know, so maybe it's a slightly
So the overlap, like this is basically this slide. So like the overlap is deliberate, and if implemented perfectly, will give a perfectly accurate simulation, basically.
Right.
So
okay, suppose to come back to this example, if you say that the classical resources needed to be unbounded to get the exact result, right? So then
yes, exactly.
How this would compare if you're kind of aiming for some finite precision?
Yeah. This is basically what I was saying, that for exact simulation you'd need, maybe you'd have an infinite advantage. But then if you look at the actual simulation you achieve, there'll be some error, and then I guess you can go back and look at, to get something like that, how many classical bits would you need.
And the graphs in her talk were inexact.
Yeah, sorry, I'm slow in catching up.
So maybe I missed it because I was late. Do you have to make any assumptions on like the state or the process you try to find? Like, is it completely blank?
So it's pretty general, but I mean it's we have some assumptions that it's like time invariant, so that if you divide your sequence into two parts, like you make a cut somewhere and you look at the past and the future, then that conditional probability distribution of the future given the past has to be the same no matter where you make that cut. And then in terms of the simulators that we're looking at, so we also have this property that is called unifilarity, which basically means if you know the memory, like if you know what causal state you're in at some point, like for these optimal models, and then you know what's been emitted afterwards, you will always be able to update your memory. And so basically you don't like weirdly split into several branches or something. And I had this slide about like the type of simulators that we consider is basically these ones where you can map a past into a memory, and then you have a systematic action on the memory to sequentially produce the outputs.
Okay, I don't see any more hands raised. I will abuse this to ask one last question, because now I think your discussion made it much clearer for me. It's really cool. So, but then, because I was asking myself, because you were saying, yeah, there's even an unbounded advantage already in small systems.
Yep.
And the obvious question is like, why didn't you choose a system
Yeah.
that shows this?
I mean,
And So is it the difficulty of the machine learning, or is the precision of the qubit measurements in the IBM Q, or?
you mean for this last part,
Yeah,
or
for
because
the
because
accuracy.
because okay, so for the accuracy, I mean.
Like, what's the roadblock? Why can't we already make it really?
Because
Yeah.
the number of
So basically depends on, like we looked at some Markovian, and then non-Markovian, like ones where your Markov order, like of that renewal one, right, the Markov order was equal to n, this process parameter. But even there, as we went to larger n, we needed longer data sets to train. So, I mean, I guess training would become difficult, but yeah. And for the earlier stuff, we did actually, I spent a little bit of time thinking about implementing one of those processes with like an unbounded advantage, like in terms of the memory. We kind of thought about some experimental setups, but we just never got to sort of complete that. And I mean, they are experimentally a bit more difficult than the ones we did.
Okay, excellent. I see no more questions, so let's thank NORA again.